In 2003, an architect named Adrian Smith picked up his phone in his Chicago office. The voice on the other end had an unusual request. They wanted to build the tallest building in the world. Not just a tall building, the tallest. Taller than anything that had ever been built before. Smith worked for a firm called Skidmore Owings, and Merrill, one of the most respected architecture companies in the world. They'd designed famous skyscrapers before, but this was different. The client didn't just want tall, they wanted impossible. And here's the part that sounds unbelievable. They needed the design in 3 weeks. 3 weeks! Most skyscraper projects take years just to get through the initial design phase. Years. Architects spend months studying the site, running calculations, sketching hundreds of options. 3 weeks is barely enough time to think through the basic concept, let alone create detailed plans for the tallest structure ever built. But Smith said yes, and that's when things got interesting. Instead of doing what most architects would do, looking at other tall buildings, studying what worked before, Smith did something unexpected. He started looking at flowers, specifically a desert flower. It grows wild in the Arabian Peninsula, where Dubai is located. Most people call it a spider lily because of its unusual shape. Why would a flower matter for a skyscraper? That seems like a strange place to start. But Smith had realized something important. This flower had already solved the biggest problem that tall buildings face: wind. When you're building something 800 meters tall, wind isn't just an annoyance. It's a serious threat. At that height, wind speeds can reach over 200 kilometers per hour. That's hurricane force. And wind doesn't just push on a building, it creates something called vortex shedding. Basically invisible spiral patterns in the air that can shake a building violently. In the worst cases, these forces can actually tear a building apart. Engineers have been struggling with this problem for decades. How do you build something tall enough to touch the clouds without letting the wind knock it down? The spider lily had figured it out millions of years ago. The flower has 3 petals arranged in a Y shape. When desert winds hit it, and those winds can be fierce, the shape confuses the airflow. The wind can't push the flower over because it can't get a good grip. The air splits apart, flows around the petals in different directions and loses its power. Smith looked at that Y shape and had a realization. What if a building could do the same thing? It sounds simple when you say it like that, but it was revolutionary. Nobody had built a super tall building with that kind of shape before. Most skyscrapers are rectangular or square because that's easier to design and construct. But Smith was proposing something completely different. He started sketching. The base would be a Y shape, just like the flower, but as the building rose higher, the shape would change. It would step back, getting narrower as it climbed. Each setback would change how the wind hit the structure. The wind would never be able to establish a rhythm. It would be like trying to push someone who keeps moving unpredictably. You can't build up momentum. Now, while Smith was sketching in Chicago, something important was happening in Dubai. The city was transforming at an incredible pace. In the 1960s, Dubai was a small port town. Maybe 40,000 people lived there. Most of them made their living from fishing or pearl diving. The city had some oil, but not much. Nothing like the massive oil fields in other parts of the Gulf. By 2003, when Smith got that phone call, Dubai had exploded to over 1 million people. Skyscrapers were sprouting up everywhere. The city had become a major business hub. But there was a problem on the horizon. Dubai's oil was running out. The leaders of Dubai knew they couldn't rely on oil forever. They needed a new plan. The ruler who would soon lead Dubai had a vision. He wanted to transform Dubai into a global destination. A city so impressive, so iconic that people would travel there just to see it. But how do you make a city iconic? How do you get the world's attention? You build something impossible. The ruler understood something important about modern cities. In the age of television and internet, you need a symbol. Paris has the Eiffel Tower. New York has the Statue of Liberty. Sydney has the Opera House. These aren't just buildings or monuments. They're the first image that comes to mind when you think of those cities. Dubai didn't have that symbol. Not yet. The tower would be that symbol. The project wasn't just about building a tall tower. It was about putting Dubai on the map. It was about proving that a small city in the desert could compete with anywhere else in the world. But wanting to build the tallest structure ever and actually doing it are two very different things. As Smith worked on his designs in those 3 weeks, he was collaborating closely with structural engineers. The lead engineer was a man named William Baker. Baker's job was to figure out if Smith's flower-inspired design could actually stand up. Could you really build something that tall with a Y shape? Would it be stable? Would it survive wind, earthquakes, the sheer weight of its own structure? Baker ran the calculations. He built computer models. He tested the design virtually thousands of times, and he came back with an answer. Yes, it could work. But it would require some serious innovation. The structural system they came up with is called a buttressed core. Imagine 3 wings arranged in a Y pattern, all connected to a central hexagonal core. Each wing supports the others. If wind pushes on one wing, the other 2 hold it steady. It's like a tripod, inherently stable because the weight is distributed in 3 directions. This was completely different from how most skyscrapers are built. Usually tall buildings have a rectangular core with columns around the outside, but the tower would essentially be 3 buildings in one, all supporting each other. By the end of those 3 weeks, Smith had created something that had never existed before. A design inspired by nature that could, in theory, become the tallest structure in human history. But theory and reality are different things. The design was approved. The client, a development company called Amar Properties, loved it. The project got the green light. Construction would begin in 2004, and that's when the real challenges started. Because drawing a building on paper is one thing. Actually building it is something else entirely. Nobody had ever pumped concrete 800 meters into the air. Nobody had ever dug foundations in desert sand that could hold 500,000 tons. Nobody had ever installed elevators that could travel that high. Nobody had ever figured out how to get water, electricity, and sewage systems to work at those heights. All of those problems still needed to be solved, and some of them seemed impossible. Adrian Smith had designed a flower that could touch the sky. Now, thousands of engineers and workers would have to figure out how to make it real. Here's a question nobody had answered before. How do you pump concrete 800 meters straight up? It sounds like a simple problem. You've got concrete on the ground. You need it at the top. Just pump it up, right? But it's not that simple. Not even close. Concrete is heavy. Really heavy. A cubic meter of concrete weighs about 2,400 kilograms. That's roughly the weight of a small car. And concrete is a strange material. When you first mix it, it's liquid enough to flow. But the moment you mix it, a chemical reaction starts. The concrete begins to harden. It's a race against time. The higher you pump concrete, the more pressure you need. Think of it like drinking a milkshake through a straw. If the straw is short, it's easy. But if you had a straw that was 800 meters long, you'd need incredible suction just to get the milkshake moving, and if you waited too long, the milkshake would thicken and get stuck. That's basically what engineers were facing with the tower, except instead of a milkshake, they had tons and tons of concrete, and if it hardened inside the pumping equipment, they'd have a massive, expensive disaster on their hands. The engineering team started looking at the numbers. The previous world record for vertical concrete pumping was about 450 meters. That record was set in 2003 at a building in Taipei. To reach the top of the tower, they'd need to pump concrete at least 600 meters, maybe more. They'd be breaking the world record by over 150 meters. Nobody had equipment designed for that. Nobody had even tested whether it was possible. So they brought in a German company called Putzmeister. Putzmeister makes heavy-duty concrete pumps, the kind used for massive construction projects. But even they had never built a pump that could push concrete that high. They'd have to design something completely new. The pump they eventually created was called the BSA 14000. It was a monster. The pump could generate pressure up to 200 bars. To put that in perspective, a car tyre is usually inflated to about 2 bars of pressure. This pump was creating 100 times that much force. But even with this incredible pump, there were problems. Big problems. The first problem was temperature. Dubai is hot. Really hot. In summer, daytime temperatures regularly hit 50 degrees Celsius. That's 122 degrees Fahrenheit. And heat makes concrete set faster. Much faster. When concrete is mixed, it starts a chemical process called hydration. Water in the mix reacts with cement, and that reaction generates heat. The hotter it is outside, the faster this reaction happens. In Dubai's summer heat, concrete could start hardening in less than an hour. If concrete hardened inside the pumping pipes, those pipes would be ruined, the pumps would be destroyed, and they'd have to tear everything apart and start over. That could delay construction by months, maybe longer. So the engineers came up with a solution that sounds almost crazy. They would only pour concrete at night. Every single pour. Night after night. For years. At night, Dubai's temperature drops to maybe 30 degrees Celsius. Still hot by most standards, but much better than 50. That lower temperature gave them more time. Instead of having 60 minutes to work with, they might have 90 minutes. Maybe a bit more. But even that wasn't enough. They needed to buy more time, so they decided to add ice to the concrete. Yes, actual ice. They built a cooling plant right on the construction site. This plant made ice constantly, 24 hours a day, 7 days a week. The ice was crushed into small pieces and mixed directly into the concrete as it was being prepared. The ice would melt, cooling the concrete down and slowing the hardening process. Think about the logistics of that for a second. They were making tons of ice every single day, in one of the hottest places on Earth, just to keep concrete from setting too fast. The cooling plant became one of the most important facilities on the entire construction site. But temperature was just one part of the problem. There was also the issue of the concrete itself. Regular concrete wasn't strong enough for this project. The base of the tower would have to support incredible weight. Eventually, around 500,000 tons, normal concrete would crack under that kind of pressure. They needed something much stronger. So engineers developed what they called high-performance concrete. This wasn't just regular concrete with some extra cement thrown in. It was a completely different formula. They used special additives, carefully selected materials, and a precise mix of ingredients that took months to perfect. The concrete they created had a compressive strength of up to 80 megapascals at the lower levels. To give you some context, normal concrete used in houses might have a strength of 20 to 30 megapascals. This stuff was nearly 3 times stronger. But creating strong concrete in a lab is one thing. Making it work in the real world, on a construction site in extreme heat, while pumping it 600 meters into the air, that's something else entirely. Every batch of concrete had to be perfect. The mix had to be exactly right. Too much water, and it would be weak. Too little water, and it wouldn't flow through the pumps. The ice had to be added at just the right moment. The temperature had to be monitored constantly. And remember, they had a 90-minute window. That was it. Here's how it worked. A concrete truck would arrive at the site. The concrete would be mixed with ice and loaded into the pump. The pump would start pushing the concrete up through a series of pipes that ran alongside the building as it rose. The concrete would travel up, 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 hundreds of meters into the air until it reached the level where workers were pouring that day. At the top, workers would guide the concrete into place. They'd spread it, level it, and make sure it filled all the forms properly. Then they'd wait for it to set enough before they could build the next level. This process happened every single night, for 5 years. In 2007, they reached a major milestone. They successfully pumped concrete to a height of 606 meters. It was a world record. Nobody had ever pumped concrete that high before, and even today that record still stands. But achieving that record wasn't just about having powerful pumps. It was about coordination, timing, precision. The concrete trucks had to arrive exactly on schedule. If a truck was late, the previous batch might start hardening before the next one arrived. That would create a weak point in the structure, a seam between old and new concrete that could fail under pressure. The ice plant couldn't break down. If it did, they'd lose their cooling system and wouldn't be able to pour that night. That meant delays, lost time, extra costs. The pumps had to work perfectly. If a pump failed while concrete was in the pipes, everything in those pipes would harden. They'd have to cut the pipes apart and clear them out. More delays, and the workers at the top had to work fast and accurately. They were often working in tight spaces in the dark, hundreds of meters above the ground. One mistake could compromise the entire structure's integrity. It's hard to overstate how difficult this was. They were pushing the absolute limits of what was possible with concrete construction. Every night was a test. Every pour was a risk. The construction team poured about 330,000 cubic meters of concrete over the course of the project. If you put all that concrete together, it would weigh about 800 million kilograms. That's roughly the weight of 170,000 elephants. And every single cubic meter has to be pumped up, sometimes 600 meters into the air, in the middle of the night before it hardened. There were close calls. Sometimes the concrete would arrive warmer than expected, and they'd have to rush to get it placed before it set. Sometimes equipment would malfunction, and engineers would have to make quick decisions about whether to continue or stop the pour. Sometimes the weather wouldn't cooperate. Even at night, temperatures could stay high, shortening their working window. But somehow, night after night, they made it work. The team working on this included concrete specialists from around the world, engineers from Germany, the United States, South Korea, and other countries came to Dubai specifically to work on this problem. They'd share knowledge, run tests, and constantly refine their process. They also did something interesting with the concrete formula. As the building rose higher, they changed the mix. The concrete at the base was the strongest. It had to support the most weight. But concrete higher up didn't need to be quite as strong because there was less weight above it. So they adjusted the formula to save money and make the concrete easier to work with at higher levels. This also helped with the pumping. Slightly less dense concrete at higher elevations meant less pressure was needed to push it up. It was a small advantage, but at those heights, every little bit helped. By the time they finished the concrete work, they'd set not just one record, but several. Highest vertical concrete pour, largest amount of concrete used in a single building, strongest concrete mix used in a real construction project. The tower was pushing boundaries in every direction. But here's something that often gets overlooked. All of this had to happen while the building was still being designed. You see, they started construction in January 2004, but the final design wasn't completely finished. As they built the lower floors, engineers were still working out details for the upper floors. They were literally building and designing at the same time. That meant the concrete team had to be flexible. Sometimes specifications would change. Sometimes they'd learn something from pouring one level that would change how they approached the next level. It was a constant process of adaptation and problem solving. And through it all, they were racing against time. The project had a deadline. The ruler wanted the building completed by a specific date. Every night they couldn't pour concrete was a night of lost progress. Every problem that delayed them put the whole timeline at risk. But they did it. Against incredible odds, dealing with heat and pressure and tight deadlines, they pumped concrete higher than anyone had ever done before. They created a structural core that could support the tallest building in the world. The concrete problem had been solved, but it was just the first of many challenges. Because before they could pump concrete up, they had to dig down, way down, and that would create a whole new set of problems. Before the tower could go up, it had to go down, way down. The foundation had to support something that would eventually weigh about 500,000 tons when finished. That's roughly the weight of 100,000 elephants standing on top of each other. All of that weight pressing down on a relatively small area of ground. But here's the problem. Dubai is built on sand, not solid rock. Sand. If you've ever been to a beach, you know what sand does under pressure. It shifts, it moves, it's unstable. You can build a sand castle, but the moment a wave hits it, it collapses. Now imagine trying to build the world's tallest building on that same material. It simply won't work. So the engineers faced a fundamental challenge. How do you anchor the world's tallest building in sand? How do you make sure it doesn't slowly sink into the ground over the decades? The answer is, you don't build on the sand. You go through it. You dig down until you find something solid, something that can actually hold the weight. And in Dubai, that meant going deep. Really deep. The construction team started excavating in January 2004. They dug down 50 meters. That's about 15 stories into the earth. Imagine a 15-story building, but underground, in reverse. That's how deep they went. They removed thousands and thousands of tons of sand and loose material. Massive excavators worked around the clock. Dump trucks hauled away the sand constantly. The excavation alone took months. They were essentially creating a giant hole in the ground. A hole big enough to fit several Olympic swimming pools. But reaching 50 meters down was just the beginning. Once they hit that depth, they started drilling even deeper. They needed to install foundation piles, basically huge concrete pillars that would go down into the earth and grip solid bedrock. These piles would be the building's real foundation, the thing that would actually hold it up. They drilled 192 piles. Each pile was about 1.5 meters in diameter. That's wide enough that you could stand inside one if it was hollow, and each pile went down another 50 meters below the bottom of the excavation. Do the math on that. The excavation went 50 meters down. The piles went another 50 meters below that. The foundation system extends 100 meters into the earth. That's deeper than a 30-story building is tall. The piles had to go that deep because they needed to reach bedrock. The sand and loose sediment in Dubai can be dozens of meters thick in some places. Below that is weak rock that still can't support much weight. But if you go deep enough, you eventually hit solid bedrock. Ancient stone that's been compressed for millions of years. That's what the piles needed to grip. Installing these piles was incredibly difficult. They used a drilling technique called bored piling. A massive drill bores down into the ground, creating a hole. As it drills, they pump water or special drilling fluid down to cool the drill bit and carry away the material being excavated. Once the hole reaches the right depth, they lower a steel reinforcement cage down into it, then fill the entire hole with concrete. Each pile took days to complete, and they needed 192 of them. The piling work alone took many months. But here's something interesting. The foundation isn't centered perfectly under the tower. It's offset slightly. Why would they do that? It seems like the foundation should be right in the middle, directly under the center of the building. But remember, the tower isn't a simple rectangular tower. It has that Y shape. Each wing of the Y creates different loads. The weight isn't distributed evenly. So the engineers had to calculate exactly where the centre of gravity would be for the entire finished building. Then they positioned the foundation to match that. It's not in the geometric centre of the building's footprint, it's where the weight actually balances. On top of the piles, they built what's called a raft foundation. This is essentially a massive concrete slab that spreads the weight of the building across all 192 piles. The raft is 3.7 metres thick. That's thicker than the ceiling height in most apartments. Pouring the raft foundation was one of the largest continuous concrete pours in history. They couldn't pour it in sections because that would create weak seams. It had to be one continuous pour. They worked for 24 hours straight, bringing in concrete truck after concrete truck, until the entire raft was poured. Over 12,000 cubic metres of concrete went into that raft. But even with all that engineering, the deep excavation, the 192 piles, the massive concrete raft, there was still a question nobody could answer with complete certainty. Would the building sink? Not collapse, not fall over, just sink, slowly settle into the ground over time. All buildings settle a little bit. When you put that much weight on the ground, there's always some compression. The soil underneath gets squeezed, and the building might drop a few centimetres over the first few years. That's normal and expected. But with the tower, engineers were worried about differential settlement. That's when different parts of the foundation settle at different rates. If one side of the building sank a few centimetres more than the other side, the entire tower would lean. And a leaning tower that tall would be catastrophic. So they did something very clever. They installed sensors throughout the foundation, dozens of them. These sensors measure movement down to the millimetre. They can detect if one part of the foundation is settling faster than another. They can measure if the building is tilting even slightly. These sensors have been monitored constantly since construction began. Engineers check the data regularly, and here's what they've found. The building does move, but barely. We're talking about tiny amounts. Less than you'd measure with a normal ruler. The building has settled a little bit, but evenly. All parts of the foundation settled at roughly the same rate. That means the tower is staying level. The foundation is doing its job. But here's something that surprised even the engineers. The building doesn't just move vertically. It also moves horizontally. Not because of the foundation, because of wind. At the top of the tower, the building can sway up to 1.5 metres in strong wind. That might sound alarming, but it's actually intentional. Engineers designed it to sway. A completely rigid building would crack and break under wind pressure. A building that can flex slightly absorbs the wind's energy and survives. But that sway creates stress on the foundation. When the top of the building moves 1.5 metres to the side, that motion creates forces that travel all the way down to the ground. The foundation has to handle not just vertical weight, but also these horizontal forces. That's another reason why the foundation needed to be so deep and so strong. It's not just holding the building up, it's holding the building steady as it sways in the wind. There's also the issue of groundwater. When you dig 50 metres down in Dubai, you're going below the water table. Water seeps into the excavation from the surrounding soil. If they hadn't dealt with this, the foundation hole would have filled with water, so they installed a dewatering system. This system uses pumps to constantly remove water from around the foundation. Even today, years after construction finished, pumps are still running to keep water from building up around the foundation. If those pumps ever failed, water could seep in and create pressure against the foundation walls. That pressure could cause problems over time. The foundation work also had to account for Dubai's geology in another way. The ground in Dubai is salty, very salty. Thousands of years of seawater and desert minerals have created soil with high salt content. Salt is corrosive. It can attack concrete and steel over time, weakening them. So all the concrete used in the foundation had to be specially formulated to resist salt corrosion. They used special types of cement and added protective chemicals to the mix. The steel reinforcement bars, the rebar that gives concrete its strength, were coated with protective materials to prevent rust. These seem like small details, but they matter. A building is only as strong as its foundation. If the foundation fails, nothing else matters. All the engineering genius that went into the tower above ground would be worthless if the foundation couldn't hold it up. And the foundation isn't just holding up a building. It's holding up restaurants, apartments, offices, a hotel, observation decks, mechanical systems, thousands of people every day, and all the furniture, equipment, and materials inside. The total weight is staggering. The engineers running the foundation project knew they were working on something unprecedented. Nobody had ever built a foundation for a building this tall. There were no textbooks to follow, no previous examples to study. They were figuring it out as they went, using physics, engineering principles, and a lot of very careful calculations. By the time the foundation was complete, they'd moved enough earth to fill multiple football stadiums. They'd drilled 100 meters into the ground. They'd poured thousands of tons of specialized concrete. And they'd created a foundation system that could support 500,000 tons. But the foundation was just the beginning. Now they had to figure out how to deal with the invisible enemy that threatens every tall building. Wind. Wind at ground level is one thing. Wind at 800 meters is something else entirely. At the top of the tower, wind speeds can hit 240 kilometers per hour. That's Category 4 hurricane force. Winds strong enough to tear roofs off houses, uproot trees, and send debris flying like missiles. But the problem isn't just the speed. It's what the wind does to the building. When wind hits a tall structure, it doesn't just push against it and move on. It creates complex patterns of airflow that can be incredibly destructive. The biggest threat is something called vortex shedding. Here's how it works. Imagine wind hitting a rectangular building. As the wind flows around the sides, it can't stay attached to the surface. It peels off and creates spiral vortices, like invisible tornadoes spinning off alternating sides of the building. One vortex forms on the left, then one on the right, then left again, creating a rhythmic pattern. These vortices push and pull on the building in a regular rhythm, and here's where it gets dangerous. If that rhythm matches the building's natural frequency, the rate at which it naturally wants to sway, the building can start oscillating violently. It's like pushing someone on a swing. If you push at just the right moment each time, the swing goes higher and higher. For a building, this can be catastrophic. The oscillations can grow so large that the structure literally tears itself apart. In the 1970s, engineers started understanding just how serious this problem was. There were buildings that had to be evacuated on windy days because they swayed so much that people inside got motion sickness. Some buildings had to be retrofitted with dampers, basically shock absorbers for buildings, to reduce the motion. So when the team designing the tower looked at their plans, they knew wind would be the biggest challenge. A building this tall, standing alone in the desert with no other structures to block the wind, would face absolutely brutal conditions, and they needed to solve this problem without adding massive dampers or other heavy equipment. Extra weight meant a stronger foundation, more concrete, higher costs. The ideal solution would be built into the shape of the building itself. That's where the Y shape came in, and it's more clever than it first appears. Remember, the building's shape isn't constant as it rises. The Y-shaped floor plan changes. The building steps back 26 times as it climbs toward the sky. From the ground, these setbacks are hard to see. The tower looks relatively smooth, but each setback changes the building's cross-section. Here's why that matters. When wind hits the building at ground level, it encounters a certain shape. As the wind travels upward, the shape keeps changing. The wind can't establish a stable pattern because the building is constantly presenting a different profile. It's like trying to push someone who keeps moving unpredictably. You can't build up momentum because you never know where they'll be next. The wind flows around one setback, starts to organize into vortices, then immediately hits a different shape that disrupts those vortices before they can form properly. The result? Vortex shedding still happens. You can't eliminate it completely. But it never gets organized enough to become dangerous. The vortices form chaotically at different frequencies, and they cancel each other out instead of reinforcing each other. But the engineers didn't just guess that this would work. They had to prove it. And proving it required some serious testing. They built scale models of the tower. Not small desktop models. These were precise replicas several meters tall, built to exact specifications. Every setback, every proportion, every detail had to be perfect, because even small differences could change how the wind behaved. These models were taken to wind tunnel facilities. A wind tunnel is exactly what it sounds like. A large tunnel where you can generate controlled wind and measure what happens. The models were tested in wind tunnels in Canada and other locations around the world. Engineers blasted these models with wind from every possible direction. Wind from the north, south, east, west, and every angle in between. They tested different wind speeds. They measured how the model moved, how it twisted, how forces were distributed across the structure. They ran thousands of tests. Each test generated data. Lots of data. How much did the model sway? Where were the stress points? Did certain wind directions create more problems than others? The test revealed some surprising things. The Y shape worked even better than expected. Not only did it prevent dangerous vortex shedding, but it also reduced the overall wind force on the building by about 25% compared to a traditional rectangular tower of the same height. But the tests also showed that the building would move. At the very top, under strong wind conditions, the tower could sway about 1.5 meters from its center position. That's significant. If you were standing on the 160th floor during a windstorm, you could actually feel the building moving beneath you. Now, 1.5 meters of movement might sound terrifying, but engineers had a different perspective. This was good news. A building that moves is a building that's absorbing energy instead of resisting it. It's flexible, not brittle. It bends instead of breaking. The key was making sure the movement was slow and controlled. Fast, jerky movements would be dangerous and would make people inside feel sick. But slow, gradual swaying, even 1.5 meters, is something the structure can handle safely. To achieve this controlled movement, the tower uses what's called a buttressed core structural system. This was a relatively new concept when the building was designed, though it's been used more since then. Here's how it works. The building has a hexagonal central core made of concrete. This core is incredibly strong and stiff. From this core, 3 wings extend outward in that Y shape. Each wing has its own concrete walls and columns, and crucially, each wing is connected to the other 2 through the central core. Think of it like a tripod. If you push on one leg of a tripod, the other 2 legs hold it steady. The tower works the same way. When wind pushes hard on one wing of the Y, the other 2 wings help resist that force through their connection to the central core. This system distributes wind loads much more efficiently than traditional designs. In a typical rectangular skyscraper, wind force on one side has to be transferred to the other side through the core. But in the tower, the load is distributed 3 ways simultaneously. The structural engineer who designed this system, William Baker, described it as a vertical cantilever. The whole building acts like a diving board, stiff at the base where it's anchored, more flexible at the top where it's free. This is actually ideal for resisting wind, but there was another aspect of wind that engineers had to consider, the impact on the building's facade. The tower has about 26,000 glass panels covering its exterior. That's a lot of glass. And at 800 meters high, those panels face incredible wind pressure. The glass had to be strong enough not to shatter, even in hurricane-force winds, they used specially engineered glass, thick, laminated panels that could handle high pressure and extreme temperature variations. Each panel was tested individually before installation. If even one panel failed, it could become a deadly projectile falling from hundreds of meters up. The glass panels also had to deal with something called wind-induced pressure differences. On the windward side of the building, the side the wind hits, air pressure increases. On the leeward side, the side sheltered from wind, pressure decreases. This creates a pressure difference across the building. If windows weren't designed properly, this pressure difference could actually suck the glass panels out of their frames on the leeward side. Engineers had to design the mounting system to handle both pushing and pulling forces. Temperature was another factor. During the day, the sun heats the glass panels. They expand. At night, they cool and contract. Over a year, Dubai's temperature can range from about 15 degrees Celsius in winter to 50 degrees Celsius in summer. The glass and the aluminum frames holding it have to expand and contract without breaking or coming loose. The facade system uses special joints that allow for this movement. The panels can shift slightly without damaging the structure. It's another example of designing for flexibility rather than rigidity. There's also an interesting detail about how wind affects people inside the building. Even though the building moves only about 1.5 meters at the very top, sensitive people can feel that movement. It's not violent or sudden. It's more like being on a boat in gentle waves, but some people find it unsettling. To minimize this effect, the building was designed with a high natural frequency. That means it sways slowly. The full back and forth cycle takes several seconds. Slower movements are less noticeable and less likely to cause discomfort than fast movements. The highest occupied floor is 163. People live and work up there every day. Most of them never notice the swaying. But on particularly windy days, some residents report seeing water move slightly in glasses or feeling a very subtle sensation of motion. It's perfectly safe, but it's a reminder that they're living in a structure that's constantly responding to natural forces. Engineers also had to consider something called wind-induced acceleration. This isn't about how much the building moves, but how quickly that movement changes. Rapid acceleration is what makes people feel sick. By designing the building to sway slowly and smoothly, they kept acceleration within comfortable limits. All of this wind engineering was critical to the project's success. Without solving the wind problem, the tower couldn't have been built. The forces at that height are simply too great for traditional designs. But here's what's remarkable. The solution was largely architectural, not mechanical. They didn't have to fill the building with heavy dampers or complex systems. The shape itself, that Y-form inspired by a desert flower, solved most of the problem naturally. Of course, there are still some mechanical systems to help. The building has tuned mass dampers on certain floors, basically heavy weights that move in opposition to the building's sway, helping to dampen the motion. But these are supplementary. The primary wind resistance comes from the shape and structure. The wind engineering of the tower has since influenced dozens of other tall buildings around the world. The buttressed core system is now used in many super tall towers. The idea of using setbacks to disrupt vortex shedding has become common practice, but solving the wind problem created new challenges. One of the most difficult was something that might seem simple: elevators. Because when you build something this tall, getting people up and down becomes a complex puzzle. The tower has 57 elevators. That sounds like a lot until you realise the building is 163 floors tall. Do the math. Most office buildings have one elevator for every 4 or 5 floors. The tower has one elevator for roughly every 3 floors, and it still isn't enough. During peak times, morning rush when people are arriving for work, evening when they're leaving, there are still waits. But the problem isn't just about having enough elevators. It's about physics. You can't just run an elevator cable from the ground floor to the 163rd floor, at least not easily, and here's why. Elevator cables are heavy, really heavy. A typical elevator cable is made of braided steel. It's incredibly strong, but that strength comes with weight. If you tried to run a cable 800 meters long from ground level to the top of the tower, the cable itself would weigh several tons. Now here's the problem. The motor lift in the elevator doesn't just have to lift the elevator car and the people inside, it also has to lift the cable. And if the cable weighs several tons, you need an enormously powerful motor just to move the cable, never mind the elevator itself. The motor would have to be massive, it would consume incredible amounts of energy, and the cable would be under such enormous tension that it might stretch, or even snap. The whole system becomes impractical, so engineers came up with a different solution. They divided the building into zones. Think of it like a vertical subway system with transfer stations. You take one elevator to a sky lobby, an intermediate floor where you get off, then transfer to a different elevator that takes you higher. The building has 3 main sky lobbies, and each one serves as a hub for elevators going to different zones. This system solves the cable weight problem. No single elevator needs a cable longer than about 500 meters. That's still a lot, but it's manageable. The cables are lighter, the motors are smaller, and the whole system works more efficiently. But it creates a different challenge: coordination. If you're trying to get to the 120th floor, you might take one elevator to the 43rd floor sky lobby, then transfer to another elevator that goes the rest of the way. If the second elevator isn't there when you arrive, you have to wait. If transfers aren't coordinated properly, the whole system bogs down. The elevator control system in the tower is incredibly sophisticated. It uses computer algorithms to predict traffic patterns and position elevators where they'll be needed. During morning rush hour, more elevators are sent to the ground floor. During lunchtime, elevators are distributed more evenly. The system constantly adapts. The elevators themselves are impressive pieces of engineering. The main service elevators can hold 12 to 14 people. Some are double-decker. They have 2 cars stacked on top of each other, serving 2 floors simultaneously. This effectively doubles capacity without needing more elevator shafts. And they're fast. The elevators travel at 10 meters per second. That's 36 kilometers per hour. For comparison, most elevators in normal buildings travel at maybe 3 or 4 meters per second. But even at 10 meters per second, it still takes nearly 2 minutes to reach the observation deck on floor 124. 2 minutes might not sound like much, but think about standing in an elevator for that long. It feels like forever. Most elevator rides last 30 seconds or less. To make those 2 minutes more comfortable, the elevators have screens showing views of Dubai and information about the building. It's a distraction technique. Give people something to look at so they don't get anxious about being in a box climbing hundreds of meters into the air. There's another issue with elevators in super tall buildings. The building sways, remember? And if the building sways, the elevator shafts sway too. Normally an elevator runs on guide rails. Metal tracks that keep the car moving straight up and down. But in the tower, those guide rails can't be completely rigid. They have to allow for the building's movement. Engineers design the guide rail system with special joints that permit slight horizontal movement. The elevator car can shift a tiny bit side to side as the building sways. Most passengers never notice this, but on very windy days, if you pay close attention, you might feel a subtle sideways motion in addition to the upward movement. The elevator doors also had to be specially designed. When the building sways, the elevator shaft moves, but the floor you're getting off on moves too, and they might not move at exactly the same rate. The doors needed enough clearance to open and close properly, even when there's slight misalignment. Then there's the air pressure problem. At 500 meters or higher, air pressure is noticeably lower than at ground level. As you ride an elevator up, the air pressure around you decreases. Your ears pop, just like on an airplane. This creates discomfort for passengers, so the elevator cars are slightly pressurized. Not to sea level pressure, that would require too much energy, but enough to reduce the pressure change. It's a compromise. Your ears might still pop a little, but it's not as severe as it would be otherwise. The air pressure issue also affects the elevator shafts themselves. As an elevator car rises quickly, it's essentially a piston moving through a tube. It pushes air ahead of it and creates a vacuum behind it. In a regular building, this isn't a major problem, but in a building 800 meters tall, the air pressure changes can be significant. Engineers had to design ventilation systems in the elevator shafts to equalize pressure. There are vents at various levels that allow air to move around the elevator car, preventing excessive pressure buildup or vacuum formation. There's also the issue of emergency situations. What happens if the power goes out? You've got 57 elevators, potentially full of people, stopped somewhere between floors. The tower has multiple backup power systems. There are diesel generators that kick in automatically if the main power fails. These generators can run the elevators, at least some of them, to safely bring people down. But even with backup power, evacuating the entire building via elevators would take hours. That's why there are also emergency stairs. The stairwells run the entire height of the building. If you absolutely had to, you could walk down all 163 floors. It would take a long time and would be exhausting, but it's possible. Firefighters train specifically for the tower. In 2025, Dubai's civil defense set a world record by climbing the building in full firefighting gear, including a 15-kilogram oxygen cylinder, in just over 52 minutes. That's incredibly fast, but it shows the challenge. In an emergency, getting firefighters to the upper floors quickly is difficult. The elevator system also had to account for the different uses within the building. The lower floors are a hotel. Above that are residential apartments. Higher up are corporate offices. At the very top are the observation decks and mechanical floors. Each of these sections has different traffic patterns. Hotel guests are coming and going at all hours, often with luggage. Residents follow more predictable patterns, leaving for work in the morning, returning in the evening. Office workers create rush hour peaks. Tourists visiting the observation decks come in waves throughout the day. The elevator system needed to handle all of these different traffic flows efficiently. Some elevators serve only the hotel, others are dedicated to residential floors. Express elevators run directly to the observation decks without stopping at intermediate floors. It's a carefully orchestrated system. There's also a set of service elevators, larger cars used for moving furniture, supplies and equipment. These elevators are essential for maintaining a building this size. Imagine trying to renovate an apartment on the 100th floor. You need to get materials up there somehow. The service elevators make that possible. One interesting detail: the elevator machinery rooms are distributed throughout the building rather than all being at the top or bottom. This is because of the zone system. Each zone of elevators needs its own machinery room with motors, control systems and cable management equipment. These rooms are located at the sky lobbies and other strategic floors. The total travel distance of all the elevator cables combined is staggering. If you added up the length of every elevator cable in the building, it would be many kilometers, and all of those cables need regular inspection and maintenance. Teams of elevator technicians work in the building constantly, checking systems, lubricating cables, testing safety mechanisms. The elevators also have sophisticated safety systems. If a cable breaks, which is extremely rare, but systems are designed for worst-case scenarios, there are multiple backup cables. And if all cables failed, the elevator has emergency brakes that grip the guide rails and stop the car. Passengers don't think about any of this when they step into an elevator. They press a button and expect to be transported smoothly to their destination. But making that simple experience work in a building this tall required solving dozens of complex engineering problems. The elevator system in the tower pushed the boundaries of what was possible with vertical transportation. Since then, elevator technology has continued to advance. Some newer buildings have elevators that travel even faster or use innovative cable-less systems. But when the tower was built, its elevator system was state-of-the-art. Getting people up and down was just one challenge of making the building functional. Another challenge that's often overlooked is even more basic: water. How do you get water to flow 800 meters upward? And once it gets there, how do you deal with everything that comes back down? Here's something most people don't realize. The tower isn't just an observation tower. People actually live there. There are 900 residential apartments spread across floors, 44 to 108. And living that high up comes with some very strange realities. First, there's the time issue. During Ramadan, Muslims fast from sunrise to sunset. They break their fast the moment the sun sets. But here's the thing, sunset happens at different times depending on your altitude. If you're on the ground floor of the tower and the sun sets, you can eat. But if you're on the 150th floor, the sun is still visible. You can still see it out your window, glowing on the horizon. You're so high up that the curvature of the earth means sunset happens later for you than for people below. Islamic scholars had to issue a special ruling about this. Residents on higher floors must wait an additional 2 to 3 minutes before breaking their fast. Time literally moves differently at different heights in this building. It's a strange thought. Two people living in the same building, celebrating the same religious observance, but doing it at different times because one person is higher up than the other. Then there's the practical stuff that people don't think about. Water. You turn on a tap and water comes out. Simple, right? Except when you're 500 meters above the ground, getting water to that tap is incredibly complicated. You can't just pump water from ground level all the way to the top. The pressure required would be enormous. The pipes would need to be incredibly thick to handle that pressure. And even if you managed it, the water pressure at lower floors would be dangerously high. It would blow apart regular faucets and fixtures. So they did something clever. They installed water tanks every 30 floors or so. Water is pumped from ground level to the first tank. Then another pump moves water from that tank to the next one higher up. It's a relay system. Water moving from tank to tank, climbing the building in stages. By the time water reaches an apartment on the 100th floor, it's been through several tanks and pump stations. Most residents have no idea this is happening. They just turn on the tap and water comes out. But behind the walls, there's an incredibly complex system making that simple action possible. Sewage works in reverse, but it's actually more complicated. You can't just let sewage fall straight down under gravity. At those heights, the falling water would build up so much speed that the pressure would blow the pipes apart when it hit bends or junctions. So the sewage system also uses a relay method. Wastewater flows down to collection tanks at regular intervals, then pumps carefully move it to the next level down, controlling the flow and pressure. It's unglamorous, but essential. And here's something nobody talks about. Trash. The building generates tons of garbage every day. 900 apartments, plus a hotel, offices, restaurants, and observation decks with thousands of daily visitors. All of that creates waste. You can't just throw trash down a chute from the 150th floor. The garbage bags would hit the bottom like bombs. The impact would be destructive, and the smell would be overwhelming. Instead, they installed a pneumatic waste system. It's basically a series of tubes running through the building. You put your trash in a special chute, and it gets sucked through pipes using air pressure, like a reverse vacuum cleaner. The trash is pulled down through the system and collected at a central location in the basement. It's the same technology used in some modern hospitals and large facilities, but scaled up dramatically. The system can handle different types of waste: regular garbage, recyclables, food waste. all separated into different tubes. Living in the tower means dealing with other unusual realities too. You can't open the windows, ever. At those heights, the wind would be too dangerous. Even if the glass could withstand the pressure, opening a window would create air pressure differences that could shatter other windows or damage the building's climate control system. So the entire building is climate controlled and sealed off from the outside world. You have these incredible views. You can see the entire city, the desert beyond, the Persian Gulf sparkling in the distance. But you're trapped behind glass. You can look, but you can't feel the air or hear the sounds from outside. Some residents describe this as peaceful. They love the quiet, the controlled environment. Others say it feels isolating, like living in a beautiful aquarium. One man has made the tower his empire. George Neramprambel, originally from India, owns 22 apartments in the building. People call him the king of the tower. His story is remarkable. He started his career selling used goods, basically recycled materials and second-hand items. Through decades of hard work and smart business decisions, he built a successful company. Now he owns more residential space in the tower than almost anyone else. Some of his apartments are rented out. Others he keeps for himself and his family. Owning 22 apartments in the world's tallest building is a powerful status symbol, but it also represents an incredible financial investment. Apartments in the tower can cost anywhere from a few $1,000,000 to over $28 million for the premium units. But even George, with all his wealth and all his apartments, faces the same strange realities as every other resident. He can't open his windows. He experiences time differently during Ramadan. He's dependent on a complex system of pumps and tanks for basic water supply. There's also the issue of the shadow. The tower casts an enormous shadow. At certain times of day, that shadow stretches for kilometers across Dubai. Buildings and neighborhoods in the shadow experience noticeably cooler temperatures, sometimes several degrees cooler than areas in direct sunlight. Some people actually like being in the tower's shadow during Dubai's brutal summer. But if you're living in a building that suddenly spends half the day in shadow because the world's tallest tower was built nearby, you might feel differently. Property values in the shadow path were a concern during planning, though the impact turned out to be less severe than some feared. For the residents inside the tower, there's a different shadow effect. Depending on which side of the building your apartment faces, you might get intense direct sunlight for hours or relatively little natural light. The Y shape means that some apartments have spectacular views but challenging sun exposure. The building's orientation was carefully considered during design. The architects tried to balance views, sun exposure, and the structural requirements of the Y shape. But with 900 apartments, not everyone gets the perfect orientation. There's also the issue of furniture and moving. Imagine you've just bought an apartment on the 95th floor. Now you need to move in. Your furniture has to come up through these service elevators we talked about earlier. Large items, beds, sofas, dining tables, have to fit in the elevator and fit through your apartment door. Some residents have discovered that certain furniture pieces they wanted simply wouldn't work. Too big for the elevator, or too awkward to maneuver through the building's corridors. There are specialist moving companies in Dubai that handle high-rise moves, and they charge premium prices for dealing with the challenges of the tower. Then there's the daily routine. If you live on the 100th floor and you forgot something in your car, going back to get it isn't a quick trip. You're looking at a 10-minute elevator journey each way, plus walking time. Some residents keep detailed mental checklists before they leave their apartments, because forgetting something becomes a major inconvenience. Grocery shopping is another consideration. If you buy a week's worth of groceries, you're carrying them through the lobby, into an elevator, possibly transferring to another elevator at a sky lobby, then down a corridor to your apartment. Many residents use delivery services, but even delivery people have to navigate the building's elevator system. Despite these challenges, living in the tower remains highly desirable. It's one of the most prestigious addresses in Dubai. The building offers amenities that few other residential towers can match. Luxury pools, fitness centres, private lounges, concierge services. And then there are the views. There's simply nothing else like them. Residents on higher floors can see weather systems approaching from dozens of kilometres away. They watch clouds form and dissipate. During fireworks displays, and Dubai loves its fireworks, residents in the tower have front row seats to the entire city's celebration. Some residents report that living that high changes your perspective. The city below looks like a model, with tiny cars and miniature buildings. Problems that seemed large feel smaller when you're literally above them. It's a psychological effect of altitude, a sense of detachment and distance. But that detachment comes with a price. Some residents, especially those with children, talk about feeling disconnected from normal life. Taking kids to a park means planning around elevator schedules. Having friends visit requires explaining which elevators to take and which sky lobby to transfer at. There's also a subtle sense of vulnerability. You're completely dependent on the building's systems. If the elevators fail, you're stuck. If the water system malfunctions, you have no water. If there's a fire, evacuation is complicated. Most residents trust the building's engineering and safety systems, but that dependency is always there in the background. The building operates like a small city. It has its own security force, maintenance teams, cleaning crews, and management staff. There are thousands of people working in the building every day, keeping systems running and services flowing. For residents, it's like living in a vertical community. You see the same people in elevators, in the lobby, in the amenity areas. Some residents form friendships with their neighbours. Others prefer privacy and anonymity. The building is large enough to accommodate both types. One thing almost all residents mention is the reaction they get when they tell people where they live. "I live in the tower" is a statement that always generates responses. Sometimes awe, sometimes curiosity, sometimes envy. But behind the prestige and the incredible views, life in the tower is about adapting to a unique set of constraints and systems. It's living in a space that pushes the boundaries of what's possible, which means dealing with challenges that don't exist anywhere else. The tower represents the ultimate expression of vertical living, but it also shows the limits and complications that come with building and living at such extreme heights. And this reality, the gap between the dream and the daily experience, would become even more apparent during a crisis that nearly prevented the building from opening at all. In November 2009, the tower stood nearly complete. The spire was installed. The glass was in place. Workers were doing final touches on the interior. The building was weeks away from opening, and then Dubai's economy collapsed. The 2008 global financial crisis had started in the United States with the housing market crash. Banks failed. Stock markets plummeted. The crisis spread across the world like a contagion. But few places were hit harder than Dubai. Dubai had spent the previous decade transforming itself at an incredible pace. The city had borrowed massive amounts of money to fund its transformation. Somewhere around $80 billion in debt. That's not a typo. 80 billion. The strategy was simple. Borrow money, build impressive projects, attract businesses and tourists, make enough money to pay back the loans and keep growing. It had worked brilliantly for years. Dubai was booming. Construction cranes filled the skyline. Property values kept climbing. But the 2008 crisis broke that cycle. Suddenly businesses weren't expanding. Tourists were cutting back on travel. Investors were pulling money out. Property prices crashed. In some areas, they dropped by 50% or more in just a few months. Dubai's government-owned companies had borrowed billions to fund projects. Now those loans were coming due, and there wasn't enough money to pay them back. Construction projects across the city froze. Half-built towers stood abandoned, their cranes silent. And the tower, still called Burj Dubai at the time, faced a terrifying question. Could Dubai even afford to open it? The building had cost about $1.5 billion to construct. That's just the construction cost. It doesn't include the land, the infrastructure, as the years of planning. The developer, Emaar Properties, had invested an enormous amount of money into this project, but Emaar was in trouble. The company's stock price had collapsed, property sales had dried up, and opening the tower wouldn't be cheap. The building needed to be staffed, maintained, marketed. There were finishing touches that still required millions of dollars to complete. Behind the scenes, panic was setting in. Dubai had bet everything on becoming a global destination. The tower was supposed to be the crown jewel of that strategy. But what if the crown jewel never opened? What if it just stood there, empty and unfinished, as a monument to failed ambition? In late November 2009, the crisis reached a breaking point. Dubai World, one of the government's major investment companies, announced it couldn't pay its debts. It needed to restructure about $26 billion in loans. The announcement sent shockwaves through global financial markets. People started questioning whether Dubai could survive. Dubai needed help, fast, and there was only one place to turn: Abu Dhabi. Abu Dhabi is the capital of the United Arab Emirates. It's where most of the country's oil wealth is concentrated. While Dubai had been building skyscrapers and tourist attractions, Abu Dhabi had been sitting on massive oil reserves, accumulating wealth quietly. The relationship between Dubai and Abu Dhabi has always been complicated. They're both part of the same country, but they have different approaches and sometimes different priorities. Dubai is flashy and ambitious. Abu Dhabi is more conservative and traditional. There's a rivalry there, even if it's usually polite. Now, Dubai needed Abu Dhabi's help, and that created a very awkward situation. Negotiations happened behind closed doors. Dubai's leaders met with Abu Dhabi's leaders, including the president of the United Arab Emirates and ruler of Abu Dhabi. On December 14, 2009, Abu Dhabi announced it would provide a $10 billion bailout. $10 billion. It was one of the largest financial rescues in Middle Eastern history. The money came with conditions, though those conditions were never fully made public. But one condition would become very public, very soon. The tower's grand opening was scheduled for January 4, 2010. Preparations continued despite the financial uncertainty. Invitations had been sent to dignitaries and media from around the world. It would be one of the biggest opening ceremonies ever held. On the day of the opening, thousands of people gathered around the tower. Fireworks were prepared, light shows were programmed. The world was watching. The ruler took the stage to give a speech. Everyone expected him to talk about Dubai's achievement, about vision and ambition, about reaching for the sky. And he did. But then he made an announcement that shocked everyone watching. The tower would no longer be called Burj Dubai. It would be called Burj Khalifa, named after the ruler of Abu Dhabi. Even people close to the project didn't know this was coming. The name change was announced live, in front of the world. Suddenly, Dubai's greatest achievement bore someone else's name. The symbolism was impossible to miss. The world's tallest building, Dubai's crown jewel, had just been renamed as payment for a bailout. Some saw it as a gracious gesture, honouring the president and recognising Abu Dhabi's support. Others saw it as humiliation. Dubai forced to give up even the name of its most iconic building. The ruler handled it with dignity. In his speech, he emphasised unity within the United Arab Emirates, the importance of cooperation between Emirates, and gratitude for Abu Dhabi's support. But you could sense the awkwardness in the moment. For years afterward, people in Dubai would sometimes still call it the Burj Dubai. Old habits die hard. But officially, permanently, it was now the tower. The financial crisis and the name change added a layer of complexity to the building's story. This wasn't just a tale of engineering triumph anymore. It was also a story about the price of ambition, about what happens when dreams outpace resources, about dependency and pride. But here's the interesting thing. The building did exactly what Dubai needed it to do. Despite the financial crisis, despite the name change, despite the worldwide recession, people wanted to visit the tower. When it opened, the observation decks were immediately popular. People from around the world planned trips to Dubai specifically to see the tower. Within a year, Dubai's tourism numbers started recovering. The city's real estate market began to stabilize. New businesses opened, the airport expanded. The crisis wasn't over, but the worst had passed. The tower became one of the most photographed buildings on Earth. Every New Year's Eve, the tower hosts a spectacular light and fireworks show that's broadcast worldwide. Millions of people watch it live, and millions more see clips online. That kind of global exposure is priceless marketing for Dubai. In 2011, the tower got even more attention when Tom Cruise filmed a sequence for Mission Impossible Ghost Protocol on its exterior. Cruise actually climbed the building's outside 123 floors up, hanging from the glass with Dubai spread out below him. The scene was terrifying and spectacular, and it put the tower in front of hundreds of millions of moviegoers. The building generates significant revenue directly. Observation deck tickets, restaurant reservations, event rentals. But its real value is indirect. It's a symbol. It puts Dubai on the mental map for people who might never have thought about visiting the Middle East. It says, this is a place where extraordinary things happen. By 2012, Dubai's economy was growing again. By 2015, it was thriving. The financial crisis became a memory, a difficult period that the city had survived. And the tower stood as a reminder that even in the worst times, even when money runs out and bailouts are needed, some achievements endure. There's a certain irony in all of this. The building was meant to prove that Dubai didn't need anyone else, that the city could achieve the impossible on its own. But the financial crisis proved the opposite, that Dubai, like anywhere else, is subject to economic forces beyond its control, that sometimes you need help, that pride has to give way to pragmatism. The name is a permanent reminder of that lesson. Every time someone says the name, they're acknowledging Abu Dhabi's role in Dubai's survival. But the story of the tower isn't complete without addressing the people who actually built it. The thousands of workers who poured the concrete, installed the glass, welded the steel, and turned architectural drawings into physical reality. Their story is less celebrated, and it's much darker, because behind the gleaming glass and record-breaking statistics lies a human cost that's often left out of the official narrative. The tower wasn't just built with money and engineering. It was built with the labour of migrant workers who face conditions that many would consider exploitation. And that story deserves to be told too. 22 million man-hours went into building the tower. That's a staggering number. If one person worked 40-hour a week, it would take them over 10,000 years to accumulate that many hours. But it wasn't one person. It was thousands. At the peak of construction, about 12,000 workers were on site every day. Most of those workers came from far away: India, Pakistan, Bangladesh, the Philippines, Nepal. They came to Dubai because they had heard the pay was good, better than back home at least. But when many of them arrived, they found something very different from what they had been promised. Here are the facts. Most construction workers on the tower earned between $4 and $8 per day. Not per hour, per day. For 12-hour shifts in heat that regularly exceeded 50 degrees Celsius, $8 a day works out to about $240 a month. In countries like India or Bangladesh, that's actually decent money. Enough to support a family back home. That's why the workers came. They weren't looking to get rich. They were looking to send money back to their families, to pay for their children's education, to build a better life. But the reality on the ground was often brutal. Many workers lived in labour camps on the outskirts of Dubai. These camps were far from the gleaming city centre, tucked away where tourists wouldn't see them. In some camps, dozens of men shared a single room. Bunk beds lined the walls. There was minimal privacy, limited air conditioning, and basic facilities. The camps weren't unique to the tower project. They housed workers from construction sites all across Dubai. But the workers building the world's tallest tower were often living in conditions that stood in stark contrast to the luxury they were creating. The workday started early. Buses would pick up workers and drive them to the construction site. They'd work through the morning, break for lunch during the hottest part of the day, then work again into the evening. In summer, even with the break, the heat was dangerous. Heat exhaustion and heat stroke were constant risks. Safety standards were supposed to be in place. Workers were supposed to have protective equipment, regular breaks, and access to water. But enforcement was inconsistent. Some contractors followed the rules carefully. Others cut corners to save money and meet deadlines. Then there's the passport issue. Many workers had their passports confiscated by their employers when they arrived in Dubai. This practice is technically illegal in the United Arab Emirates, but it's been widely documented by human rights organisations. Why would employers take passports? Control. If a worker's passport is locked in an office somewhere, that worker can't leave the country. They can't quit their job and go home even if conditions are terrible. They're essentially trapped until the employer decides to return the passport. This creates a power imbalance that's hard to overstate. The worker is completely dependent on the employer for everything: their job, their housing, their legal status in the country, and their ability to leave. That's a recipe for exploitation. In March 2006, halfway through construction of the tower, something unusual happened. Workers rioted. About 2,500 workers stopped work and started protesting. They smashed equipment. They blocked access to the construction site. Security forces were called in. The entire project ground to a halt. Why did they riot? Unpaid wages. Some workers hadn't been paid in months. They'd been working 12-hour days in extreme heat, living in crowded camps, sending their paychecks home to support their families. Except the paychecks weren't coming. The story made international news. Human rights organisations issued statements. The Dubai government got involved. Eventually some wages were paid. Work resumed. But the underlying conditions didn't fundamentally change. 4 workers died during the construction of the tower. That's the official number. 4 deaths over 6 years of construction, involving 12,000 workers at peak times. By the standards of construction projects, especially one this ambitious, that number is actually relatively low. But some human rights organisations have questioned whether the official count is complete. Record-keeping for migrant workers in Dubai has been criticised as inadequate. If a worker died from heat stroke a day after leaving the site, would that be counted as a construction death? If a worker in a labour camp died from an illness, would that be investigated? The truth is, we don't know for certain. The official number is 4. The real number might be higher. In 2011, a year after the building opened, something happened that's hard to forget. A worker who had been part of the construction crew jumped from one of the upper floors. He died instantly. He didn't leave a note. We don't know exactly why he did it. Maybe it had nothing to do with his work on the tower. People face personal struggles for all kinds of reasons, but the symbolism was impossible to ignore. A man who helped build the world's tallest monument to human achievement, who spent years of his life creating something that millions of people would marvel at, chose to die by falling from it. That image haunts the story of the tower. It's a reminder that behind every great structure, there are human beings with human struggles. And sometimes those struggles become unbearable. Here's the uncomfortable truth. The tower stands as proof of what humans can accomplish when we push the boundaries of engineering and ambition. But it also stands as a reminder of who pays the price for that accomplishment. The workers who built this tower, who dug the foundation, poured the concrete, installed the glass, welded the steel, they made it possible. Without their labour, the tower would not exist. But most of them will never experience what they created. They can't afford to visit the observation deck. They don't live in the luxury apartments. They built it, but it wasn't built for them. This isn't unique to the tower. Construction projects around the world, especially large ones, often rely on migrant labour working in difficult conditions for low pay. The pyramids of Egypt were built by workers whose lives we barely understand. The great cathedrals of Europe took generations to complete, with countless workers whose names were never recorded. There's a pattern throughout human history. Monuments and great structures often require suffering to create. The question is whether we acknowledge that suffering or ignore it. The tower's official story emphasizes engineering triumph, architectural vision, and economic ambition. Those things are real and worth celebrating, but the worker's story is also real and deserves acknowledgement. In recent years, the United Arab Emirates has made some reforms to labour laws. There are stronger regulations about working conditions, pay schedules, and worker rights. Enforcement has improved in some areas, but activists argue there's still a long way to go. Dubai has also become more sensitive to international criticism about labour conditions. The city wants to be seen as modern and progressive, and stories about worker exploitation damage that image. There's pressure from international organisations, from media scrutiny, from global public opinion, to treat workers better. Whether that pressure translates into real change on the ground is debated. Some workers report better conditions in recent years. Others say problems persist. The truth is probably somewhere in between. Some things have improved, but significant issues remain. For the workers who built the tower between 2004 and 2010, those potential future improvements came too late. They worked under the conditions that existed at the time. Some of them look back with pride at being part of something historic. Others remember it as the hardest period of their lives. Many of those workers are still in Dubai, working on other construction projects. Dubai continues to build aggressively. New towers, new attractions, new developments. The demand for construction labour hasn't slowed down. Some of the men who built the tower are now building the next generation of Dubai's skyline. Others went home. They saved enough money to return to their families, to start small businesses, to give their children opportunities they never had. For them, the years in Dubai, despite the hardship, were worth it because of what they could provide for their families. There's no simple moral to this part of the story. It's complicated. The workers made choices. They chose to come to Dubai, chose to take these jobs, chose to endure difficult conditions for economic opportunity. But those choices were made within constraints. When your options are extreme poverty at home or hard labour abroad, is that really a choice? The tower is both triumph and tragedy. It's a testament to what human ingenuity can achieve, and it's a reminder of what human ambition sometimes costs. When you look at the tower rising into the sky, gleaming in the desert sun, it's worth remembering that it was built by human hands. Thousands of people, working 12-hour days far from home, creating something that would outlast them. Their names aren't engraved anywhere. There's no memorial listing the workers who built it. But their labour is embedded in every floor, every beam, every pane of glass. The tower stands because they built it. And 15 years later, that tension still hasn't been resolved. The tower remains the world's tallest building, a symbol of achievement and ambition. but it's also a symbol of the human cost that sometimes accompanies great projects. The final question about the tower isn't really about the past, it's about the future. Will it remain the tallest, or is something even bigger coming? And if we do build taller, will we learn from the mistakes of the past, or repeat them? The race for height never truly ends, and the tower's reign, as dominant as it's been, won't last forever.